So thank you for the introduction. The short answer to the question is that James Bond has no idea. And now we can move on to the longer answer. So about 2,500 years ago, ancient Greeks enjoyed entertaining themselves by asking the question of what would happen if you took something. Everyone always says an apple, cut it in half, then in half again, and kept going like that. Now there are two obvious possibilities. Either you'll be cutting this apple until the end of time, or eventually you'll hit something that you can no longer cut, which they called an atom, and I very belatedly realized is cognate with lobotomy and tomography. Now let's ask a slightly different question. What if instead of cutting something in half, we take something and make progressively smaller copies of it? So let's take the Mona Lisa, which many people who see it in person say is already smaller than they expected it to be. You can make it into a postcard or a postage stamp, but then things become a bit more interesting. The next one is the smallest copy anyone painted by hand. I discovered people have a thing about making really small copies of the Mona Lisa. The one after that is made out of folded DNA and is about 1/100th of the width of a human hair. And the one after that is not the Mona Lisa, but as far as I know, the smallest ever image of a human being, where every single lump in this picture is an individual atom. So the takeaway here is that not only as you go smaller, the technology you need to make this copy becomes way more intricate and difficult to do, but also the character of the copy itself changes. One can imagine a recognizable pixelated Mona Lisa of the scale of that boy, but if you wanted to make it 10 times smaller again, your best approximation would probably be a triangle, and nobody would be able to tell that what you wanted to make is the Mona Lisa. Now, what happens if you make progressively smaller copies of the same thing is not actually an idle question. Because if you were ever faced with the dilemma of whether you should buy a new computer now or wait 6 months until new hardware comes out, you've been invested in the process of making progressively smaller electronics. Now, we've done pretty well with it. We've moved from computers the size of a building to computers that fit in our pockets in the scale of a couple of decades. Currently, we are at around 70 atoms, so 7 nanometers at the smaller scale of our transistor. Intel promised us 20 atoms approximately this year. It got delayed. But the point is that we're pretty close to the point where this atomic pixelation becomes important, and we can't move much further down without considering it. So what I do in my research is jump to the very end of this line and study what happens when electrons flow through about the smallest electrical component you can imagine, which is a lump of atoms, where a lump of atoms is frequently called scientifically a molecule. Well, the thing about molecules is that there's lots of them. They can be very different. We're very good at making them. You can ask chemists and they will make you essentially whatever you want. And also, by definition, every molecule of the same compound is identical, which is very good for experimentalists. So molecular electronics is a fairly large field where people study how can you make electrical components out of single molecules, what they do and how well they perform. I approach it from a slightly different perspective and ask, why does this particular molecule operate in this particular way? And how do we know what's going on inside of it? And you can imagine that in order to make better electronic devices out of molecules, we need both these types of questions. Now, actually, why does something we have work the way it does is a fairly new question in engineering. Because if you think of any normal microscopic device, why it does what it does is never really a scientific question, because theoretically you can always take it apart and look inside. It may not be very easy, and putting it back together again can be difficult, but it's not really a scientific issue. Where with a molecule, it's actually fundamentally impossible to see what's going on inside. The reason for that is something to do with the very known story of Schrödinger's cat, which in a closed box exists in some sort of weird state, which is neither being alive or being dead. And when we open the box, we then discover that the cat is either being alive or the cat has died. The thing with that is that even if we were able to make a microscope good enough that we could observe individual electrons hopping through this poor molecule, while we were looking at the molecule with our fantastic microscope, which we don't yet have, it would behave in an entirely different way from a molecule that is not being observed. So we have to find some other ways around it. The part of science I use for it is called thermodynamics, which seems slightly counterintuitive because thermodynamics is the science of how your hot cup of coffee gets colder, or how to make a steam locomotive. But actually, it makes a lot of sense because thermodynamics can be reframed as the science of how can we make predictions about something that exists inside of a black box. If we think about it, if we take any normal object of thermodynamics, say steam in a steam engine, it actually consists of an unimaginable number of individual particles, each doing its own thing. And it's fundamentally impossible to know all the details about the system. So what we can do instead is invent parameters such as temperature, pressure, and so on, which describe the collective behavior without knowing the precise individual details. And this works so well that, say, your car engine starts every single time, and you never find yourself in a situation where you can't start your car because the molecules inside haven't aligned just the right way. However, when we want to study thermodynamics of a small system, unlike most other sciences where if something has few parts to it, it's easier to analyze, in thermodynamics it's exactly the opposite. The reason for that is that most of thermodynamic quantities have to do with averages. Say temperature is the average energy of a particle. And averages don't work very well when you average over a small number of things. For example, average income is a very useful quantity when you want to compare between countries or cities or areas within a city. This is where rich people live, this is where poor people live. But if you know the average income of 3 people, you can't really tell if one of them is rich and has all of it and 2 of them have nothing, or maybe they all have 1/3 of it. You just don't know, and it doesn't tell, and tells you a lot less than the average income of an area in a city. So part of my job is trying to figure out how to extend thermodynamics into small systems. And to show what it is exactly I'm doing, so it's just an example of one particular work where I had a rather large molecule with electrons jumping through it. We can experimentally measure current as a dependence on different voltages. And then it was my job to analyze this data, extract these lines. And the main takeaway is that you get some nice numbers from these lines. And the nice numbers to take away is 1, 4, and 4. And now I'll walk you through what I do with these numbers. Imagine you have a box with a hole in it, so you can throw different things in it. And on this box, there's also a magic post-it, which tells you how many different configurations can whatever's inside of the box have. So if the box is empty, the number is 1, because there's only one way of being empty. Now, if we throw a ball in it, the number will still be 1, because we don't care about where the ball is and how it's oriented. So it's just a ball in a box. It's still one state. Now, if we throw in a coin, the number will become 2 because the coin can be tails up or heads up. So this number tells us something about what it is we're throwing inside. But imagine we throw a coin inside and we get the number 4. How could that be? One possible solution is that there is some kind of partition inside this box, so that the coin can be heads or tails and on left or right of the box as well. Now, the point is that we can't look inside of the box, so we don't know if there is a partition. If there is a partition, we don't know if it goes front to back or left to right or diagonally. But we can imply that there is something partitioning our coins because we see the number 4. Now, having already one coin inside the box, let's throw in another one and see what happens. You can imagine that the number will grow to, well, you can think about which number you expect. But we throw another coin as experimentalists, and we still see the number 4. How could that be? One possible explanation, and tell me at lunch if you can come up with something else, is that there's also some mechanism that prevents coins from sitting at the same side of a partition. Say they like to repel from one another. Or if a coin goes into one half, now this half is closed and the second coin has to go to the other half. Then you exactly have 4 states with 2 coins in it. Now, this is the exact same logic I followed when studying what electrons are doing in this molecule. These numbers 1, 4, and 4 were the number of configurations the molecule with different electrons numbers had. So electrons behave quite a lot like coins in the sense that they have a spin and they can be either spin up or spin down. And from these numbers 1, 4, and 4, one can imply that 1 stands for an empty molecule or with some offset charge. Then if you add another 1, you have 4 because there are 2 sides on it where electrons can sit. And then you add another 1, you still have 4 because they repel strongly enough that they can't occupy the same space. So this is what I do actually looks like on the day-to-day basis. But so it's not very pleasant. But what I'm trying to do is simplify this complexity and the experimental complexity as well into these very simple parameters that can allow us to solve complicated behavior of things we can't observe as puzzles, much like the one I gave as an example. Okay, thank you.